Automatic, Addison.
In the previous tutorial, we learned how to use SLAM, simultaneous localization and mapping, to create a map of the environment while keeping track of the robot's location. Now that we have a map, it's time to take things to the next level and make our robot navigate autonomously. By the end of this video, you'll have a robot that can independently navigate from point A to point B while avoiding obstacles along the way. Here is what you will make happen in this tutorial. Autonomous navigation has numerous applications in the real world. Here are a few examples of how the concepts you'll learn in this tutorial can be applied. First, home service robots. Imagine a robot that can navigate your home, performing tasks like delivering snacks, collecting laundry, or even reminding you to take your medicine. Autonomous navigation enables robots to move around home safely and efficiently. Warehouse automation. In large warehouses, autonomous mobile robots can be used to transport goods from one location to another. They can navigate through the warehouse aisles, avoid obstacles, and deliver items to the correct storage locations or shipping stations. 3. Agriculture. Autonomous navigation can be used in agricultural robots that perform tasks such as harvesting, planting, or soil analysis. These robots can navigate through fields, greenhouses, or orchards without human intervention, increasing efficiency and reducing labor costs. Hospital and healthcare. In hospitals, autonomous mobile robots can be used to transport medical supplies, medication, or even patients. They can navigate through the hospital corridors and elevators, ensuring timely and safe delivery of essential items. Finally, search and rescue. In emergency situations, autonomous robots can be deployed to search for and rescue people in hazardous environments. These robots can navigate through the rubble, collapse buildings, or other challenging terrains to locate and assist victims. By mastering autonomous navigation, you'll be opening doors to a wide range of exciting applications that can benefit various industries and improve people's lives. Okay, now I want you to understand the configuration file. So let's open up a terminal window and let's navigate to where the YAML configuration file is located. CD ROS2 source, Yaboom ROS master, Yaboom ROS master navigation, and config. Here we are. And let's do a gedit ROS master. So you're going to do get it and then the name of the file. And with the file open, we can now explore and understand the different sections and parameters within the configuration file. I'm going to go up to the top now and we'll break down the parts that are most important for autonomous navigation. First section you'll see in most navigation parameters YAML files is AMCL, Adaptive Monte Carlo Localization. AMCL helps the robot determine its location within the map. It uses a particle filter approach where each particle represents a possible pose, position, and orientation of the robot. The parameters you can see here in the AMCL section control how AMCL updates and resamples these particles based on sensor data and the robot's motion. Key parameters include the max particles right here, 2000. See what else is important. Update min D, important, update min A. And the noise models for the motion and the robot model type. Where you can see right here, omni motion model, because we're using an omnidirectional robot. You can also use a differential motion model if you're using a differential drive robot. Very important there. The laser model type, likelihood field, but typically you won't need to modify these from the defaults. I like to use 0.05 for update min A and 0.05 for update min D. Again, have a look at my navigation configuration parameters guide on my website, where I go through each of these in greater detail. Next, we have the BT Navigator section, Behavior Tree Navigator. This section is responsible for high-level decision-making during navigation. It uses a behavior tree structure to define the logic for tasks like following a path, avoiding obstacles, and recovering from stuck situations. Moving down to the controller server, The controller server section handles the execution of the robot's motion commands. It receives the path from the planner and generates velocity commands to follow that path. So the parameters in the controller server section configure the controller plugins, okay, all in here, such as follow path. All right, we've got that right here, the path tracking algorithm. We've got the goal tolerances, both X and Y and yaw. So how tight do we want to be to our goal location? The lower the values, the tighter to the goal locations. But also the robot will have a tendency to dance around too if the localization is very poor. So it's a Goldilocks thing. Not too hot, tight, not too loose. You want it just to be just right for your robot. And we've got a lot of other different, got min X, minimum X velocity threshold, minimum Y velocity threshold. I got progress checker plugins, which monitors the robot's progress along the path. And you notice down here, we are using the MPPI controller, which is called the Model Predictive Path Integral Controller. And you can read about that online. I chose this controller because it works well for mecanum wheel robots. So you can find a high-level description of all the different controllers you can use on the Navigation 2 website. Now let's go down to the velocity smoother. See where we can find it. Where are you? Where are you? Scroll down, scroll down. Velocity smoother, where are you? Down here, line 366. This is another important node. So the velocity smoother takes the velocity commands from the controller and smooths them to ensure smooth and stable robot motion. It helps to reduce sudden changes in velocity and acceleration. So the velocity smoother section controls the smoothing algorithm. You know, you got things like the smoothing frequency. You've got the velocity limits, both max and minimum velocity, and the acceleration limits as well. So this can help when your robot is herky-jerky moving around. You can use the velocity smoother to make sure you've got nice, smooth path following and navigation. Next, we've got the planner server, which is right here on line 309. The planner server is responsible for generating paths from the robot's current position to the goal location. It uses the global cost map to find the optimal path while avoiding obstacles. The planner server section, okay, and you'll find this in pretty much every navigation parameter YAML file. It specifies the planner plugin, in this case we're using grid-based, and its associated parameters, such as the tolerance for the path search, right here on line 315. Okay. And whether we want to use A star or not, the A star algorithm. In this case, we set it to false. Now let's talk about the smoother server. The smoother server is responsible for optimizing and smoothing the global path generated by the planner before it's sent to the controller. This helps create more natural and efficient robot trajectories. Now let's go down here to the behavior server. The behavior server handles recovery behaviors when the robot gets stuck or encounters an error during navigation. It includes plugins for actions like spinning in place, spin, backup, and waiting. These sections work in harmony together to provide a comprehensive configuration for the robot's autonomous navigation system. By adjusting these parameters in the YAML file, you can fine-tune the robot's behavior to suit your specific requirements and environment. Now let's talk about the collision monitor. Where are we here? Probably going to be down here, collision monitor. There we go, collision monitor. This is a safety system that continually checks for potential collisions and can trigger emergency behaviors when obstacles are detected. Definitely want that in here. Now it's time to launch autonomous navigation. So I have a nav alias right here, nav, which runs this bash script. That's what we're going to run right now. So let's clear the terminal so you can see it clearly. NAV, that's it, and run it. So running the bash script will launch the gazebo simulator with our Yaboom ROS Master X3 robot and the necessary navigation nodes. You should see Gazebo and RViz windows open up. In Gazebo, you will see the simulated environment with the robot over here on the left, and RViz will display the robot sensor data, the map, and the navigation-related visualizations. Wait for everything to come up to initialize and for the robot to be spawned in a Gazebo environment. Okay, and once everything is up and running, you want to click the 2D pose estimate. And given where the robot is, you can see the table right here. Robot's a little bit in front of the table and to the left. So that's this table leg right here. So a little bit forward and to the left. I'm going to put here and then drag it to the right because the robot's facing towards the right. So you click, hold down, and drag to the right. And that sets the pose. We can see all of the inflations around the various obstacles, the wall specifically. So that's how you initialize the pose of the robot. You must do that before the robot can start navigating, because the navigation system needs to know the initial position and orientation, which is called the initial pose, within the map. And that process is known as localization. So again, remember the 2D pose estimate, click it, click where you think the robot is, and drag. So the robot's localization system, which is AMCL, uses that initial pose right here as the starting point. And it continuously updates the estimated position and orientation based on sensor data and movement commands. And I'm going to just reiterate that setting the initial pose is very important, because you have to give the robot a reference point to start localizing itself within the map. Without an accurate initial pose, the robot may have difficulty determining its precise location and orientation, which can lead to lots of navigation issues. And for a real robotics project, I should recommend the Isaac ROS map localization package by NVIDIA, which will enable you to automatically localize the robot based on a PNG version of the map. So that's a very cool thing you can do in a real robotics project. So you can either do it like that using a package like map localization, Isaac ROS, or you can set it manually like I did by publishing the initial pose. All right, now we are going to send a goal pose. Once the initials pose is set for the robot, you can command it to navigate autonomously to a specific goal location on the map. And fortunately, RViz provides a handy dandy button up here, the nav2 goal button. It's an intuitive way to send navigation goals. So follow these steps. So in the RViz window, locate this nav2 goal button, click it. Okay. And then move your mouse cursor to the location on the map where you want the robot to navigate. Let's navigate it over here near this little bar, just in front of it. And then click and then hold the mouse button to whatever orientation you want it to go. I'll have it facing downwards. And then release. And that sets the goal. You can see the path, that red line. Robot moving towards the goal. And as the robot moves, you will see its position and orientation updating in real time here in RViz. And once the robot reaches the goal, okay, it orients towards the goal orientation. And we can set another goal. Let's send another one between these tables over here. Excuse me. See how it created a path around the obstacle, which is the table. So zoom out, you can see the robot over here, making a curved path around that table. So each time you send a new goal pose, the robot will replan its path and navigate towards the new goal. Keep in mind that the robot's ability to reach the goal pose depends on various factors, such as the accuracy of the map, the presence of obstacles, and the configuration of the navigation stack. If the robot is unable to reach the goal pose, it may attempt to replan or abort the navigation task based on the configured behavior. Now, during autonomous navigation, you can monitor the robot's progress, path, and planning, okay, and other relevant information through the RViz visualizations right here. Okay, I love it. Because RViz, and here we've got the Navigation 2 plugin, you can see the feedback on the robot status over here, including any errors or warnings. So you can just send goals as you wish. Keep sending. And later, in a later tutorial, I'm going to show you how to do this through code. You send goals through code. And that's what you do in a real-world application. But right now, we're just using RViz, keeping it simple. Now, let's say, okay, instead of sending a single goal pose, you want to command the robot to navigate through a sequence of goals or waypoints. Waypoints are intermediate goal positions that the robot should pass through before reaching its final destination. This is useful when you want the robot to follow a specific path or perform tasks at different locations. And here's how to do it. So we've got the initial pose already set, robot's already at its goal, and so forth. We need to now click the waypoint nav through pose mode button. Click that. Okay. Now click the nav to goal button up top and click on the areas of the map where you want to place your waypoints. I'm going to place one over here. Drag. Place another one over here. Drag it. Let's place another one over here. Drag. And then place another one pretty close to the home position over here. Drag. And if we zoom in, you can see the different waypoints that we created. We created a total of 4. 1, 2, 3, 4. Zoom in. Zoom way in, way in, way in. You can see waypoint 3, actually the numbered waypoint right there. So that's the third one. Let's zoom into the second one. Waypoint 2, right there. Pretty cool. And when you are ready for the robot to start moving through the waypoints, you'll click this button that says Start Waypoint Following. And the robot will now move to the first waypoint. And if you want to visit each location without stopping, you would have clicked the Start Nav Through Poses button instead of the Start Waypoint Following button. And now you should see your robot autonomously navigate to all of the waypoints with a brief pause at each. And you can see here, goals succeeded each time we reach a new waypoint. So arrived at the 0th waypoint, sleeping for 10 milliseconds. Execute some task if you want, and you're going to navigate to the next waypoint. Robot moving to waypoint 2, then it's going to move to waypoint 3, and then 4. Now, I often like to check the CPU usage and memory usage. In general, I want to see a CPU usage and memory usage less than 80%. When you get above 80%, that's when the problems start and you get real performance issue. So I'm going to do sudo apt-get install htop. Okay, let's check it. Install. Should be fairly quick. And then type this command, htop. And let's check the CPU usage. Yeah, it's popping up pretty high now because we've got Gazebo and RViz. Got some 80%. But overall, it's around the 50 to 60% level, which is not bad. Memory is also quite low, 3.52 gigs of 15.6 gigs. Not too bad. Okay, so you can see around 50. But let's close the RViz window. RViz uses a lot of juice. So let's close that. Click X, close without saving. Okay, and you can see we had quite a bit of a drop now. Now it's around the 30 to 40%. some spikes up in there, but it's much lower now that we close RViz. Looks much better. RViz is a resource hog. And so for this reason, for the robots I develop professionally, I do not run RViz in a production environment. I only use it during development and for debugging. So that's it for this tutorial. You can Control C on everything. Thank you for watching, and I'll see you next time. Keep building.